Okay, so we introduced the idea of the chain rule, and we want to continue with that. Sometimes when we apply the chain rule to the derivative of certain functions, they are referred to as the generalized rules. So just recall here the chain rule, and it says that if we have a function y is equal to f of g of x, right, then the derivative, we'll just call it y prime, which I could also again write as dy dx, right, by this chain rule is the derivative of f, which is what we call the outer function. F prime is the derivative of f, the outer function, evaluated the inner function, times what? The derivative of the inner function. Okay. Now with the Leibniz notation, if I were to have u being the function g of x and y, the outer function is f of u, right, so that we get f of g of x when we compose those together, then dy dx, right, is dy du. This dy du is the derivative of the outer function, evaluate the inner. That's the same as this f prime of g of x times the derivative of the inner function u with respect to x. Du dx is the same as g prime of x. So this is what we've just introduced in the last video. As we generalize that, then, if I'm taking the derivative with respect to x of u to the n, where u is a function of x, then that's the chain rule, or what we sometimes call the generalized, in this case, power rule. If this was x to the n, the derivative would just be what? Bring n down, x to the n minus 1, right? Subtract 1 from the exponent. Well, here, u is not necessarily equal to x, but it is a function of x. So it's the chain rule. The derivative of the outer function is nu to the n minus 1 times the derivative of the inner function. So it's chain rule, but it's called the generalized power rule. Similarly, we have a generalized e to the x rule. We know the derivative with respect to x of e to the x is just e to the x, but the derivative with respect to x of e to the u is e to the u, that's the derivative of the outer function, evaluate the inner, times the derivative of the inner function. So the dy du part is e to the u, the du dx part is the derivative of the inner function. Generalized rule for sine. Derivative with respect to x of sine of u is cosine u, right? Derivative of sine is cosine, derivative of the outer function, times the derivative of the inner function. Okay? And this works, right? If u is equal to x, then du dx is just equal to 1, and we get our regular rules. This is the generalized rule. So we just think about that when that's really the chain rule. You might hear it called generalized rule. So let's look at these cases. Let's find the derivative dy dx in each case. So dy dx, this is power rule or generalized power rule, or the chain rule. Right? I have u is 6x plus 4 to the 7th, u to the 100th power. What's the derivative of u to the 100? That's 100 u to the 99th power. And what is u? U is the inner function, 6x to the 4th plus 7, times what? Du dx, derivative of the inner function. So du dx in this case would be the derivative with respect to x of 6x to the 4th plus 7. So the derivative of 6x to the 4th plus 7, we can do that, right? Bring the 4 down, I get 6 times 4 is 24x cubed. So if I multiply 24x cubed times the 100, my derivative is 2400, 24 times 100, x cubed, 6x to the 4th plus 7 to the 99th power. So that's chain rule, but again, we call that the generalized power rule in this case. Here's chain rule again, but it's the generalized rule for the tangent function. The outer function this time is tangent. The inner function is 4x squared plus 3x. Right? So in this case, the derivative is the derivative of tangent. What's the derivative of tangent? Secant squared. Evaluated at u, in this case 4x squared plus 3x. Times what? The derivative with respect to x of that inner function. Okay. And what is the derivative with respect to x of this stuff? Well, that's pretty easy. We've got, bring the 2 down, 8x to the first plus the root of 3x is 3. So we might write our final answer, bring this stuff in front, 8x plus 3, I have to put that in parentheses, right, times secant squared of 4x squared plus 3x. So it's chain rule or the generalized rule for tangent, which is just what? Root of tangent secant squared u times du dx times the derivative of the inner function. We'll do one more. Here's a generalized rule for cosine. Outer function is cosine, inner function e to the x. So dy dx. Derivative of the outer function. What's the derivative of cosine? Do you remember that from our last lecture set for the trig functions? Negative sine, right? Negative sine of u, right? Times what? The derivative with respect to x of e to the x. What's the derivative with respect to x of e to the x? Well, that's just e to the x. And so bringing this e to the x in front, I get negative 1 times e to the x sine of e to the x. So those are some examples. Again, these are all chain rule, but sometimes they're called generalized rules. Okay. Now, as we've developed this chain rule, and we saw in the previous video examples of the chain rule where we had like a product rule when we took the derivative of the inner function, or a quotient rule. Okay, so these things get combined in different ways. Now, I want to just look at 2 ways of finding this derivative. And actually I say quotient rule versus chain rule. It should be quotient rule versus power rule. We're going to have chain rule in both cases. So, sorry, strike that again. Product. I'm having all kinds of trouble today. Product. Product is what I want to say. Okay. So number 1, let's look at the quotient rule way. And that's, notice I have this function is a quotient, so I can just apply the quotient rule straight up. Right? Remember how that works? It's the derivative of the top function times the bottom, which is 2x minus 1 to the 4th. We don't really want to expand that out. That's going to make things very cumbersome. So leave it compact like that, minus the top function, and then times the derivative of the bottom function. And when we do that, what do you see there? I hope you see a chain rule or a generalized power rule. I've got u to the n, where n is 4, u to the 4th power. Right, so we'll be taking the derivative of that in a minute. Remember, this is still the quotient rule over what? All over the bottom function, which is 2x minus 1 to the 4th squared. Now, we can take the derivative of this fairly easily. 5x cubed derivative is what? Bring the 3 down, 15x squared. But over here then, what do we have here? This is going to be by the chain rule, right? What do? It's u to the 4th, so this 4 comes down in front. And I have what? U is what? 2x minus 1. Subtract 1 from 4, 3. There's the derivative of the outer function. Bring the 4 down. U to the 3rd. But then times what? Times the derivative of the inner function, which in this case, 2x minus 1's derivative is what? 2. Right? 2. And so this stuff, the derivative of all this becomes what? 2 times 4, 8 times 2x minus 1 cubed. So what does this bring us to? We've got 15x squared was the derivative of this thing times the 2x minus 1 to the 4th. And then I've got minus 5x cubed times 8, 2x minus 1 cubed. So this 8 and this 5 I can multiply to 40 x cubed times 2x minus 1 cubed. And then down here, what do I have? 2x minus 1 to the 4th squared. I multiply those exponents and I get 2x minus 1 to the 8th. Okay. Now, we can simplify, and we should in this case, because up top you'll notice I don't want to expand, but I can factor. Notice 15 and 40. have a common factor of 5. X squared and x cubed have a common factor of what? X squared, smaller exponent. And 2x minus 1 to the fourth, 2x minus 1 cubed, I can factor out 2x minus 1 cubed. Okay, so what's that leave me with the first one? I factored out a 5. That leaves me 3. Pulled out the x squared. And then 2x minus 1, pulled out 3 of them. That leaves 2x minus 1. Minus what? 40. I factored a 5 out of the 40. That leaves an 8. I factored out an x squared from the x cubed. That leaves an x. And I factored out the 2x minus 1 cubed. And then we can simplify what's in the hard brackets here. 3 distributed through here gives me 3 times 2x is 6x minus 3 minus 8x. And 6x minus 8x is negative 2x minus 3. I'm going to go ahead and factor out a negative 1 from this. And so if I rewrite this, I have 5x squared, 2x minus 1 cubed times negative 2x plus 3. I'm going to pull that negative out in front. So it's negative 5x squared, 2x minus 1 cubed times 2x plus 3. All over 2x minus 1 to the 8th. And so I factor the numerator. And we looked at this at the very beginning of the course when we were doing the prerequisite material. Can we factor things that arise in calculus? I talked about that. Well, we have arrived. That's what we need to be able to do. Now, not done yet. I can still do some simplifying. Right now that I've factored the numerator, do you see any common factors in the numerator and in the denominator? Yeah, 2x minus 1, right? So how do I do that? I can cancel, right? 3, I can divide numerator and denominator by 2x minus 1 cubed, and that's going to leave me what? To the 5th here. If I divide 2x minus 1 to the 8th by 2x minus 1 cubed, that gives me 2x minus 1 to the 5th. And so my final answer, simplified, is negative 5x squared times 2x plus 3, all over 2x minus 1 to the 5th power. Okay, so that took quite a bit. Had a quotient rule, and within the quotient rule we had the chain rule. Okay, so this was the quotient rule. And then I said, product rule, after changing it several times, product rule, after rewriting. So how do I rewrite this into a product from a quotient to a product? Well, remember, I can take 5x cubed divided by 2x minus 1 to the 4th is the same as multiplying 5x cubed, what, times the reciprocal. What's the reciprocal of 2x, 1 over 2x, or 2x minus 1 to the 4th? It's 2x minus 1 to the negative 4th power. So I can multiply. So method 2 here, product rule, I have to rewrite f of x as 5x cubed times 2x minus 1 to the negative 4th. Okay, so now it's just product rule, which is a little bit easier. So if I find f prime now by the product rule, it's the derivative of the first function times the second plus first function times the derivative of the second. Okay. Well, again, this one we've done is easy. The derivative of 5x cubed is 15x squared. Here is the chain rule, right? So here is the chain rule. Again, we can't get away from it. We saw it above. A little bit different form this time because instead of 2x minus 1 to the 4th, it's 2x minus 1 to the negative 4. But still, chain rule or generalized power rule. Bring the negative 4 down. 2x minus 1. Subtract 1 from negative 4. Negative 5. times the derivative of what's inside. What's the inner function? 2x minus 1. Derivative of 2x minus 1 is 2. Okay. So if I clean this up a little bit, now I've got negative 4 times 2. That's negative 8 times 5 is negative, so I'll write that minus 40 x cubed times what? 2x minus 1 to the negative 5 power. Okay, and now what? Simplify, factor. Do you see that I have two terms I'm subtracting here, right? Subtraction now. So 15 and 40, what's the greatest common factor of that? 5. X squared and x cubed, smaller exponent, x squared. And 2x minus 1 to the negative 4 versus 2x minus 1 to the negative 5. Which one do I pull out? Again, the smaller exponent is negative 5. 2x minus 1 to the negative 5 power. What's that leave? Pulling 5 out of 15 leaves 3. Factor the x squared out. And now how do I do this? 2x minus 1 to the negative 5. How do I factor that out of 2x minus 1 to the negative 4? Well, when I remultiply again these two like bases, what am I going to do with their exponents? I'm going to add them. Negative 5 plus what equals negative 4? Negative 5 plus 1 equals negative 4. So it's just to the first power here. I'm not going to write, we don't write first powers, right? It's just 2x minus 1. Okay, out of the second term, got minus here, right? So this minus sign is coming right from there. Minus what? Pull 5 out of 40 leaves 8. Pull x squared out of x cubed leaves x. And 2x minus 1 to the negative 5 out of that. Right? And this should look familiar. We saw this in the above example there. And so this I can simplify, distributing the 3. 6x minus 3 minus 8x. I get 6x minus 8x, negative 2x minus 3, or again, factoring out that negative, negative 1 times 2x plus 3. Okay. Of course, this again I can rewrite now without the negative exponent as 1 over 2x minus 1 to the positive 5. And my final result is, up top, 5x squared times a negative 1 times 2x plus 3, so that negative comes up in front, negative 5 x squared 2x plus 3, 2x plus 3 rather, over what? 2x minus 1 to the 5th. And if you look at the previous method, the previous example, here's our derivative here. We compare it, it's the same. Okay. So, question is, this can be done either way. Do you prefer just straight up using the quotient rule? Right? We didn't have to worry about those negative exponents in this case. We did have to do a little simplification at the end there, right, to get it to this final result. But there was the quotient rule. Or what? Rewrite it as a product, right, equivalent function as a product, and then use the product rule and factor and simplify. Okay. Which method is better? That was my question at the beginning. Which method is better to apply? Well, I don't know if there's a definite answer. Some of you may prefer this quotient rule, and some of you may prefer the product rule. Okay. Now, there's one exception to this question. If the numerator of the function you're taking the derivative of is a constant, in the bottom is a composition where you're going to have to use chain rule, it is much better to rewrite and use the product rule. So let me show you an example of that. This was not in my notes, but let's suppose, what about right here? What a nut. Sorry. If, let's find f prime of x if f of x is equal to this. Okay, sorry. I want to just contrast that with the previous example, right? Here the numerator was not a constant. Now it is, right? So you could certainly use quotient rule on it, but it's a much more cumbersome. So it's better to rewrite in this case as a product and use the product rule. So in other words, I would rewrite the function f of x as 7 times 4x cubed plus 5x to the negative 9 power, right? So that's the reciprocal. So these are equivalent functions, but now you say, you know, we said product rule, but I really don't need product rule because this is not a function of x. It's a constant multiple. So it's just constant multiple rule. So you see, it's even better. I don't have to use the product rule. So this 7 is a constant multiple, right? There's no need to use the product rule. Times the derivative of all this stuff, which is what? Well, it's u to the negative 9. It's a generalized power rule. Bring the negative 9 down in front. 4x cubed plus 5x. Subtract 1 from negative 9 gives me negative 10. Times the derivative of what's inside. Well, what's inside is 4x cubed plus 5x. Derivative of 4x cubed is 12x squared. Derivative of 5x is 5. Right? So this was constant multiple rule, and then we have generalized power rule, chain rule. Right? So we can clean this up a little bit. Again, this can be written as what, 1 over 4x cubed plus 5x to the 10th power. And I've got 7 times negative 9 is negative 63 times this, so my final result is negative 63 12x squared plus 5 all over 4x cubed plus 5x to the 10th. Okay. So again, this is better. Had we tried to do this just as a quotient rule, it gets rather messy in there, and it's not bad, I should say. It's not bad, but it's just a little easier to do. So if the numerator is a constant function of those two methods we were talking about before, you know, should we use the quotient rule or should we rewrite and use the product rule? We would want to rewrite. In fact, we don't have to use the product rule because our function, in this case, the top function is a constant. Basically, you know, that when we take the derivative of a constant, this part becomes 0, and this, you know, it's just a constant multiple. It's just the constant times the derivative. Okay. But if the top function is also a function of x, you know, then, you know, should we use quotient rule or should we rewrite and use product rule? It depends. I typically tend to shy away, if I can, from the quotient rule. So a lot of times I would do something like this as an alternative. Okay. In the next video, we'll look at what happens when we've seen product rule inside of chain rule. We've seen quotient rule inside of chain rule. We've seen chain rule inside of quotient rule with this example, and chain rule inside of product rule. What I want to look at in the next video is chain rule inside of chain rule. And really understand why it's called the chain rule from that. We'll do that next.